On exam 1, I discovered that one of the questions has 2 correct answers. Which I did not recognize prior to having exam 1 graded. So I'll have exam 1 regraded so that those who reported the second or alternative correct answer to this question will receive credit. In addition, I decided to make available to all of you the opportunity to earn 10 extra credit points if you identify this question. Here's an extra hint. Since bonus quiz 2 is due tomorrow, bonus quiz 1, pardon me. I haven't given you the opportunity to report this question on the back side of bonus quiz 1 so that when you submit it tomorrow at the beginning of your discussion class gathering, if you correctly identify this question, you'll get 10 additional points. Plus, I also said, if you can explain why this other answer to the question, which has been miskeyed, is correct, that'll give you another 15 extra credit points. So, since if you're going to gather this, it has to be done by tomorrow so that you can submit this along with bonus quiz 1, I have said today, see this announcement, where you'll see the announcement on Sakai telling you what I've just told you with a little bit more detail. As I said, at least I believe I said, I make every effort to see to it that you folks are not penalized for goofs which I make. So I hope this not only makes up for that difficulty, it'll give all of you the opportunity at my expense, not really, your benefit, to get some more credit. Whatever you make, I'll just have the folks, the discussion instructors, add what you've earned by way of this extra credit challenge, add that to your score for bonus quiz 1 and report it accordingly. And that'll take care of that. Now let's finish up chapter 18. As we said last time, a consideration which brings together many of the important points we wrestled with in chapter 18 involves the calculation of the hydronium ion concentration for this particularly dilute solution. This solution is so dilute that in order to correctly calculate the hydronium ion concentration, you must figure in Kw. We talked about that last time. Because if you make a determination of the max contribution to the hydronium ion molarity for this solution by acid ammonium ion, you'll find out that that number is less than 1.0 times 10 to the minus 7. But this is an acidic solution. It can't have a hydronium ion molarity less than 1.0 times 10 to the minus 7. We know it's acidic because the ammonium ion molarity is twice that of the sulfate ion molarity, and Ka ammonium ion is a good deal bigger than Kb sulfate ion. In fact, Kb sulfate ion is so small, which we also looked at last time, we can recognize that sulfate ion will really not exert any impact of notice on the hydronium ion concentration for this solution. So to proceed, we also recognize that the principal Bronsted-Lowry acid-base equilibrium in this system is a reaction between ammonium ion and sulfate ion, and that does not provide a source of hydronium ion or hydroxide ion. So we have to look elsewhere to calculate the hydronium ion concentration? Well, elsewhere it comes to us by looking at the Ka equilibrium expression for ammonium ion in conjunction with material balance and charge balance. Because when we write the charge balance equation, we've got hydronium ion in it. And if you think about it, you should recognize that it is the charge balance equation which in fact factors in Kw. It's got hydronium ion in it, it's got hydroxide ion in it. Hydroxide ion is Kw over hydronium ion. Kw is now included. Can we, before proceeding with solving, can we legitimately simplify the charge balance expression? Are there any terms from the charge balance expression as it stands on the board which we can legitimately remove? What do you think? Well, I'll remove this one. Is that fair? Well, you're probably saying, well, if he removed it, it must be fair. Why is it fair?
Because SO4 2 minus is so weak that it doesn't.
Well, the main acid-base reaction in this system is ammonium ion plus hydrogen sulfate ion. Products ammonia and hydrogen sulfate ion. We looked at the K value for that last time. It's on the order of 10 to minus 8. So given that K is 10 to minus 8 for that, on the order of, and the molarities of ammonium ion and sulfate ion are pretty damn small, you're not going to have much hydrogen sulfate ion in here. What about hydroxide ion? We can always include it if we need it. But do you think it's likely reasonable to not have to pay attention to the hydroxide ion concentration? Well, it's an acidic solution. But be careful, because this is a very mildly acidic solution. If it's very mildly acidic, how does the hydronium ion concentration compare to 1 times 10 to minus 7? How does the hydronium ion concentration compare to 1 times 10 to minus 7? Close to, but a little bit bigger. Well, that means the hydroxide ion concentration is also close to 1 times 10 to minus 7, but a little bit smaller. So we don't want to take out hydroxide ion. Now then, by taking these two expressions, and as necessary, solving for the ammonia molarity in terms of the hydronium ion concentration, you get this. And solving for the ammonium ion concentration in terms of the hydronium ion concentration, you get this. You do the arithmetic. It's not hard. It's not hard at all. But you do it. You need to practice. So we have an expression, Ka ammonium ion, 5.6 times 10 to minus 10 is equal to this. How many unknowns you got now? 1. Can you solve it? You're damn right. How am I going to solve it? I'm going to start by taking advantage of what we have already recognized. That the hydronium ion concentration in this system is small and close to 1 times 10 to minus 7. But a little bigger than 1 times 10 to minus 7. In fact, if you think about it, last time we recognized that the hydronium ion concentration cannot even be close to this number. So, we notice hydronium ion concentration is pretty damn small. So, I would suggest, not demand, but suggest, that a reasonable trial value to find out the hydronium ion molarity which satisfies this relationship. Because when this term with the right hydronium ion substituted, what number will you get? That one. Okay? I'd probably try 1 times 10 to the minus 6. And if you try 1 times 10 to the minus 6, you're going to find out it's too big. A good deal too big. So now you know hydronium ion molarity is a good deal less than 1 times 10 to the minus 6 and equal to or greater than 1 times 10 to the minus 7. You got this thing in a pretty small box already. The value which I get, 1.3 times 10 to the minus 7. Indeed, keeping with all the considerations which we have just finished discussing. But you can do the arithmetic. Now, we go to chapter 19. You were introduced to chapter 19 by way of what took place in discussion class last time. And perhaps you came to realize that for chapter 19, which bears the caption Equilibria, which involves salts of limited solubility in water, or as I have called them more simply, semi-soluble salts, I've listed 5 subcategories of topics, which together constitute the body proper of chapter 19. The first subtopic of which, subtopic A, involves calculation of salt solubility for a saturated solution of this salt. Under the simplest possible set of conditions. Why so? Like calculating the solubility for silver chloride saturated in water. Because neither silver ion nor chloride ion have properties which bring about a measurable impact on water solution pH. Chloride ion we know to be a base weaker than water, so that's not going to do anything. Silver ion has a measurable Ka. Silver ion forms this well-defined hydrate. But Ka for this well-defined hydrate is on the order of 10 to the minus 13. Practically speaking, it does nothing from a pH standpoint. How might we verify this? You go to the laboratory and get a hold of a water solution that's rich in silver ion and which contains an anion we know has no effect on solution pH. And the only common salt of silver ion which is quite soluble in water is silver nitrate. Now likely you've recognized that in 46 laboratory we only use 200 molar silver nitrate solution. Used to use 10th molar, but we don't need it that concentrated. Because the silver salts whose solubilities you investigate in 46L are very slightly soluble at best. So you don't need much silver ion in the presence of the corresponding anion, like silver ion with chloride ion, to bring about precipitation. So the 200 molar silver nitrate solution is adequate. But you could take and dissolve some more silver nitrate and raise the molarity of silver ion up to 10th molar, and you would find out that on observation of the solution pH for 10th molar silver nitrate, you would find a pH the same as deionized water solvent. What's our DI water solvent running these days in the laboratory pH-wise? About what? 6.0? That's fine. That's commonly attributed to a little bit of absorbed CO2. So we'll take it at that. That's fine. So if I dissolve the silver nitrate in fairly high molarity, like 10th molar, and I still get the same pH, well then, silver ion didn't do anything. It isn't doing anything from a pH effect standpoint. Consequence. If I have a salt whose cation component and anion component do not exert a measurable effect on solution pH, with water being the solvent, then I can calculate the solubility for that salt straight away from its KSP value. I want you to pay attention to this. One equilibrium, and that's it. That's the simplest possible case regarding salt solubility and equilibria which involve semi-soluble salts. However, thereafter, the system gets a lot more muddy because most semi-soluble salts, like teacher's favorite weapon, which is principally calcium carbonate, have an anion component, which is a Bronsted base that's a good deal stronger than water. What's the upshot of this? If I make a saturated solution of calcium carbonate in water, which by now I expect many of you have already done. How many of you are in assignment 3? How many of you have looked at the pH in laboratory of saturated calcium carbonate solution? All right, not too many. For those of you who have looked at it, what kind of pH did you get? Saturated calcium carbonate solution. pH about what?
12.6.
How much?
12.6.
12.6, no. You got calcium hydroxide. Calcium carbonate. In assignment 3, you first looked at water solutions of calcium hydroxide. Then you looked at water solution of calcium carbonate, and lastly you'll look at water solutions of calcium sulfate. The 3 salts of calcium ion of limited solubility whose chemistry you investigate in laboratory. Well, in any case, we're going to do this in a short while. Take a peek at the pH for saturated calcium carbonate solution. We'll find out that it's on the order of 10. Now, what's the upshot of this from a salt solubility standpoint? The upshot is when you want to calculate the solubility for a salt like calcium carbonate, which has got an anion, specifically carbonate ion, which is a good deal stronger base than water, you also have to pay attention to Kb for the anion. So that makes the system more complicated. Now, associated with this will be the case of often looking at a chemical equilibrium reaction for which the equilibrium constant is a composite of 2 or more fundamental equilibria. What do I mean by fundamental equilibria? Well, in Chapter 18, what fundamental equilibria did we look at? There were 3 specifically. Remember what they were? Kw, Ka, and Kb. How about that? And now, Chapter 19, the first thing you did was introduce yourself to the new equilibrium constant called or labeled KSP, which is solubility product constant. Because KSP for silver chloride, for example, is the product of these molar concentrations. That's called a solubility product constant. And you also recognized that KSP is defined by an equilibrium reaction equation with the salt on the left and the component ions on the right. If you turn it around, you still got a legitimate equilibrium, but then it's 1 over KSP. Like Ka in Chapter 18, the acid plus water, making hydronium ion and the conjugate base of the acid. I can turn that around, still at a legitimate equilibrium, but now it's 1 over Ka. So some of these things you just have to know. KSP you have to know. So given then, in chapter 19, you will often have to deal with equilibrium reactions for which the K value is not given and will therefore obligate you to calculate such. Will require you to analyze the equilibrium reaction and decide what fundamental K's is this damn thing composed of. And as things stand, what are the possible fundamental K's? I just finished naming them. KW, KA, KB, KSP. That's it. And we'll find out at the end of chapter 19, we're going to add to our bag of K tricks, KF, which stands for formation, specifically formation of a complex ion. Let's put that one on hold and wait till we get there. Like the silver water ion. That's a complex ion. It's a complex ion of silver ion glued with water molecules. So, some of you looked at this last time in discussion class, but the reports that I got back from the discussion instructors is everybody didn't get this far. And I need you to be able to do this, to be able to play this game. How do I get K for an equilibrium reaction for which the K is not supplied? Like this. Right off the bat, I can write the equilibrium constant. But how do I evaluate it? How do I get the value for the K for this thing? Pardon? Well, I look at this equilibrium reaction. I look at it. And I let this damn thing talk to me. We've said this many times, haven't we? You got to let this stuff talk to you. In other words, you got to understand it. You got to know what it means. So I'm looking at this equilibrium reaction. The first thing I see is the presence of a salt of limited solubility. Have you noticed on our information table, information sheet, there's also a list of salts of limited solubility and their KSP values? Now, we haven't used those yet, but now we're going to use them extensively. So if you got that information sheet, which I'm sure everybody has, and I hope you got it with you, if you look at that, you'll see this list of K values, KSP values. So I look at this thing, and I see as a reactant, I got the limited solubility salt silver chloride. And I look at the right, and I see as a product, I've got the limited solubility salt of limited solubility silver sulfide. So I know, before I go any further, two equilibrium constants of which this K is composed is KSP for this and KSP for this. And if I let this thing talk to me further, you see this 2? What's that mean? It's going to be KSP squared. KSP squared. Now one more thing. Will the KSP for silver chloride squared be in the numerator denominator of this? It'll be in the numerator denominator. KSP silver chloride. Ah, we have a fight. You look over there. How's KSP defined? You see this reaction? This defines KSP, doesn't it? The salt is where? The reactant side, isn't it? Is that silver chloride on the reactant side? So where is KSP squared for silver chloride in this thing? Numerator! You gotta let it talk to you. And I'm just programming you to learn how to let this thing talk to you. But silver sulfide, where's KSP for silver sulfide squared going to be in this thing? Denominator, bingo. Now we got to pay attention to something else, which comes to us from our acid-base chemistry. I've written a chemical equilibrium reaction equation on the board, but I put quotes on it. Why did I put quotes on it? Is this chemical equilibrium reaction a reasonable chemical statement? Why not?
Because sulfur.
These equilibria are all being studied in what solvent? Water. We could have a measurable molarity of sulfide ion in water? Hell no! Too strong a base. See? Acid-base chemistry. Statement: if you have not grasped acid-base chemistry, Chapter 18, there's no way you're going to get on successfully with Chapter 19. It's impossible. Because damn near everything we're going to do will not deal with these simple equilibria where you don't have to pay attention to anything beside KSP. You know me, I want to show you real chemistry. And chemistry's a lot of things, but simple ain't one of them. So, the acid-base chemistry is once again a very integral part of what we are now going to do. All right? So we go back to this and recognize that KSP squared for silver chloride is the silver ion molarity concentration squared times the chloride ion molarity concentration squared. Right? There's KSP. I want it squared. Now I got chloride ion molarity squared, so I'm going to play a game. When I play this game, have I changed the numerical value for K? Hell no, I multiplied by 1. We did this in Chapter 18, didn't we? We did this in Chapter 18 when we showed how KW relates to Ka and Kb for a Bronsted-Lowry conjugate acid-base pair, didn't we? Well, now we're going to do this kind of stuff extensively. Now, I'll check this term and check this term. The two terms which I checked correspond to KSP silver chloride value squared. Now, let's go back to silver sulfide KSP. This no good. Whoops. This is anti-entropy. All the erasers are on this side. They're supposed to be all over the place. More on that later. We know sulfide ion reacts with water, extend 100%, and in so doing makes HS minus and HO minus. And since we know you cannot have a measurable molarity of sulfide ion in water solution, here's the KSP equilibrium expression for silver sulfide. All follows from our knowledge and understanding of acid-base chemistry, which a bunch of general chemistry textbooks haven't figured out yet. They got sulfide ion molarities all over the place. As soon as I see that, out the door goes this book. Burn it if it's cold, trash bin if it's not cold. I don't want that. That's junk. And they got the nerve to charge hundreds of dollars for this stuff. No. All right? Now then, what does that thing tell us to do? Oops. This is in the way. I know there's something wrong with this. There's no 2 in front of that. 2 mole silver chloride, 1 mole silver sulfide. I knew there was something. What the hell's wrong with that? Now I see it. Okay. Pardon me. Get that 2 away from silver sulfide. So let's back off and recognize silver sulfide KSP is included in this equilibrium constant expression. First order, first power, not second power, not squared, and in the denominator. So I have it now, don't I? So now I got KSP silver chloride squared divided by KSP silver sulfide. Well, I've accounted then for all the components of this equilibrium system. Except what? Have I yet accounted for this? Have I yet accounted for this? Have I? I got an equilibrium expressions here that, like a KSP silver chloride squared divided by KSP silver sulfide. Do either of those contain hydronium ion? Do either of those contain H2S? So I'm not done yet. So I'm going to take a look at this. Okay? I'm going to take a look at this. I'm going to take a look at this. Hydronium ion molarity times HS molarity divided by H2S molarity. What's that correspond to? KaH2S. Isn't that part of this? Isn't H2S a reactant and hydronium ion a product? Bingo. So I'm going to take a line through the exponent because I'm reducing this to 1. Because this is hydronium ion molarity times hydronium ion molarity. And then I'm going to check this. And I'm going to check this. So now, in my mind's eye, I see KSP silver chloride quantity squared divided by KSP silver sulfide multiplied by KaH2S. That's what we got so far. Anything left? How about that? I look at this thing and I say, guess what? I still got hydronium ion times hydroxide ion. KW. All done. Now you can put in the numbers. This is in the notes, so you know what to do with it, and most of you have already been through it. You write it out, it's to your benefit, and you'll get K of something on the order of 10 to the 9th. Forget what the heck it is. Let me look. 5 times 10 to the 9th. Now let's let this K number talk to us. What's that say? If I go to the lab, treat a water solution containing silver ion with chloride, boom, I make the silver chloride. Okay so far? Now I'm going to take this water solution, which got silver chloride laying at the bottom, so it's really a mixture more so than a solution. A heterogeneous mixture. I'm going to take this system and add some aqueous H2S solution, say 10th molar, and shake it up. May I now expect something to happen, chemistry-wise? What is the something that I may well expect to happen? Even though silver chloride is very stable, very slightly soluble in water, does this assessment support the conclusion that if silver chloride is placed in the presence of a source of sulfide ion, like H2S is going to convert to silver sulfide? Yeah. Does this support the conclusion then that silver sulfide is a hell of a lot more stable and a lot less water soluble than silver chloride, even though silver chloride is very stable and not very soluble? Yeah, that's what that number tells us. Hey, that's 5 billion. Pretty big number. Good. Now we know what this thing means. Now, in preparation for dealing with solubility calculations, we will look at this equilibrium reaction. You think it's fair to say that this equilibrium is established if I take some calcium carbonate and shake it up in deionized water and all the calcium carbonate does not dissolve? Is that fair? For this equilibrium reaction, K equals KSP, calcium carbonate, equals 6.2 times 10 to the minus 9. Now, for silver chloride, as you saw last time in discussion class, KSP silver chloride, we'll write it down for reference, is 1.7 times 10 to the minus 10, and S silver chloride is the square root of KSP, which is 1.3 times 10 to the minus 5 molar. Fair, because silver and chloride don't do anything else. So we don't have to pay attention to the KSP equilibrium. This is what you did last time. Now let's go back and look at this. Because if the solubility of calcium carbonate is legitimately estimable from this KSP value, I can take the square root of this, I'll have the solubility of silver chloride. Calcium carbonate. Pardon me. Oh, what's the gee whiz square root of this? I've rewritten it as 62 times 10 to the minus 10. What's a gee whiz square root?
8 times 10 to the negative 5.
About 8 times 10 to the minus 5? Bingo. Now, the known value for solubility calcium carbonate at normal lab conditions is S calcium carbonate equals 1.4 times 10 to the minus 4. From that I get 8 times 10 to the minus 5. Conclusion? May I or may I not correctly calculate the solubility for calcium carbonate by just looking at its KSP? I may not. Hell, this number's twice that. So let's take a look. I got some deionized water. I got some calcium carbonate. I got some phenolphthalein. Phenolphthalein, you may recall, becomes a red-pink coloration in water solution if the pH rises above 9. Now on occasion this thing doesn't work because I haven't run enough deionized water out of the tap. And I get the deionized water that's too acidic. But I ran that for a while, so perhaps this will work. We'll wrap things up today with this. I got saturated calcium carbonate solution. Observably saturated because the damn thing is cloudy as hell, telling us that all the calcium carbonate hasn't dissolved. Phenolphthalein, and no pink color. Well, a little bit. Well, it's starting to get there. Yeah, you can see the pink? Yeah, okay. We could repeat it and make it more pink, but that's good enough. So since this stuff doesn't become this red pink until we're well above pH 9.0, we know daggone well that beside this equilibrium reaction, we also have to consider, to get at the solubility of a material like calcium carbonate, what? Kb carbonate ion. We'll pick it up from this point next time.